Okay, so today we're going to take a look at the applications for Trig, which look a lot like graphing. So for one thing, this is probably going to be one of the better application sections that you'll like because there's not a lot of variance in the problems, and if you're okay with graphing Trig, you should be fine with the questions on applications here. So let's just take a look. Before we start, there's a couple of preliminary things. So the first thing is we're just going to take a look at these graphs there to start with. So the first one is y equals sine of 2 pi over 3 x minus 1. So we'll put that equation into the x minus 1. So there's that graph. Maybe just to help you see it a little better too, here's the center line. Maybe I'll zoom in even a little more just to help us see some of those figures. Now, one thing you'll notice here, if I go back to that equation, well, you can see it. I'll also click on what I entered. And again, it's never a bad idea to be practicing with your TI-83 while I do these. But what do you notice possibly different from the other equations we've been working with previous to this? Yeah, there's a pi now inside the brackets here. So right there, there's now this pi that wasn't there before. It's kind of strange, but what do you think that does to the graph? Anybody notice something maybe possibly nicer about this graph? Yeah, exactly. That's a great way to say it. It sort of rationalizes the period. What I'll show you is I'll show you one of the graphs. So for example, one period might be, say, from from x equals 1 to x equals 4. So those black lines show one of the periods for the sine graph, and you can count 1, 2, 3 units make up the period. So this graph would have a period of 3. There's no more pi or anything in it. Okay, so let's we're going to record that down in here, that this graph has a period of 3. Which for our applications is important, right? I mean, there isn't approximately 11 pi days in the year, right? We would say 365 days, right? We have nice integer numbers usually when we deal with these. So let's take a look and see the other graph, and maybe we can find a pattern. So this time I'll do y equals 5 times cos 2 pi over 5. And again, if you've got your TI-83, you might as well be working with me here to get used to using your graphing calculator. So there's one of the graphs. And what's the period for this one? Maybe I'll block it in just so you can. There's one. Sorry. I know it's. Oh, well, I've only got one red. But anyways, the two vertical lines, they box in one cycle of this cosine graph. So what's the period of this cosine graph now become? 5, yeah. So there's 5 units now in the period of that graph. So the reason we're bringing this up is here's a handy way to figure out how to get a period that doesn't involve pi. So for example, if we were to use these horizontal stretch factors, okay, then the period would be whatever value you choose as p. So if there's 365 days in your problem, and that's going to be the period, then it would be 2 pi over 365. If there was 17 hours before the cycle returns, then it would be 2 pi over 17. Okay. So what we're going to do is we're going to try just to make a couple quick equations. The first one here having period 2, and all the pieces are given to you. The second one, however, you have to infer some of the pieces like the amplitude and the center line. Okay, so see if you can come up with a cosine equation for both of those problem descriptions. And remember, you're always looking for four things. You're looking for the amplitude, the period, the center line, and the phase shift. Okay, so see what you come up with. So I'll catch up while you're working with this. But again, all the pieces are given in the first one. So this is just a review, and do you remember how to put them together? Okay, so that would be the equation that's described by those pieces for the first one. And this is the new part here. So if we want the period to be 2, then that's how we can find it. As I mentioned, you're going to have to infer some of the pieces. So for example, if I know the maximum is 25 and the minimum is 13, the amplitude is going to be 25 minus 13 divided by 2, halfway between the minimum and maximum. So this will be 6. I also know that the center line is going to be 25 plus 13 divided by 2. So 38 divided by 2 is 19. If I want a period of 6, then the new idea we're working with would be 2 pi over 6. So of course that reduces down to pi over 3. So this would become y equals 6 cosine pi over 3 x minus 3 plus 19. Okay, so the other preliminary thing that we wanted to review before we got started was these graphs, sort of the situations we deal with in applications. Okay, so for example, in the first one, if we look at our problem in the application and we end up starting at a maximum and falling, what graph does that look like most to you? Yeah, cosine. So it would be natural choice that we would do this problem with the cosine. It's not wrong to pick sine or any other form. It's just usually easier because the graph fits that pattern best. Okay? We may find in our problem that we start at a minimum. So for example, here is a sinusoidal graph that starts at the minimum. So what does that look like to you? Yeah, it looks like a negative cos. It's the cosine graph that's been flipped vertically, so it would be negative cos x. If we're at the center of the graph, the center line and rising, you might have something like this, which looks like the sine, yeah. So this is the sine of x. And if we were at the center and falling, then that means our picture might look something like this. What do you think that could represent? Yeah, good. So we should be able to pick up one of those four choices to help us get the easiest equation. Okay. So we're going to try it in the first example and see where we get. But those four graphs are really helpful in helping us get a nice phase shift. Okay, so here's the question. It says, a Ferris wheel has a radius of 42 meters. Its center is 43 meters above the ground. It rotates once every 50 seconds. Suppose you get on at the bottom at time 0. And first what we have to do is graph what this would look like for our height above the ground. Okay, so why don't we get a picture of a Ferris wheel going here, and then we can add to it. So for example, maybe this is the Ferris wheel. And we've got some extra information we can label. So I'm going to take the one of the easy ones here. I'm going to take the radius. It says the radius is 42 meters. Anything else we can label? Sure, Kathy? Yeah, there's only 1 meter here. So let's say that's 1 meter. Anything else? Okay, it's our first crack at it, so maybe it's not quite obvious yet what's going to help us in this problem. It will also help us if we think about how far up the wheel is centered. So where is that? Where is this line right here? How tall is that? Yeah, that's 43 meters. That's the radius plus that extra meter that we had. So the middle of the Ferris wheel is going to be fixed at 43. Why do you think that might be an important feature? Yeah, that's going to turn out to be the center line of our graph because it bobs 42 meters up and 42 meters down. So what do you think 42 might represent? The amplitude. It's going to go from 42 up, 42 down, 42 up. It's going to keep bouncing above and below the 43 meter mark. So what's the tallest part that this rider will hit on the ride? 85 meters. So this height right here is 85 meters. Okay. And what's the most boring, the lamest, the lowest spot on this graph? 1 meter. So that would be our minimum. Okay. And the period of this graph, what would the period be? Yeah, 50 seconds is 1 revolution. That's going to keep repeating. Once around takes 50 seconds. So this is the period of 50 seconds. So, yeah, it's a pretty fast Ferris wheel. But anyways, if we were, it'd be a fun Ferris wheel then, we'll say. Okay? So this should start to feel like we're doing the graphing again. Right now you've got a minimum, a maximum, a center line, a period. There's a lot of stuff in here like the other graph. Let's see what this might look like in the picture. So first we need to, this axes, they're not labeled. It looks like I'm going to need to do 2 cycles, so I need at least 100 seconds. That means, let's see here, that's probably a good idea to go 20, 40, 60, 80, and 100. And then vertically, we need to represent the height, which could be at most 85. So to make it easy again, why don't we pick 20, 40, we'll go 10 for each grid mark for the scale. And now we can show what this Ferris wheel ride would look like on a graph. Okay. So for example, when we get on, we start at the bottom and we are 1 meter tall. So right at the very beginning, we're 1 meter, and that's about where the Ferris wheel would be. Okay. Okay, forget the Ferris wheel for a second. What's the next key feature? You don't need to tell me the position, you don't need to tell me the number. What's the next key spot on the trig graph that it's going to hit? If we go from the bottom to the center, right? The center is the next one we're going to hit. So just like any other graph that we were doing, why don't we add the center line to our picture? So the center line's at 43, which is probably about there. Okay. So how far over will they be when they hit the center line? 85 is quite a ways past where they'll hit the center line the first time. Sorry? 12 and a half seconds. Yeah, how did you know 12 and a half? Yeah, so this is the period. So my key points, just like we've done before, will be a quarter of that, or 12.5. So every 12 and a half seconds, they hit the next spot. So for example, 12 and a half seconds goes by, and then I will be on the center line. So probably around there. Then the next 12 and a half seconds is 25. 25 seconds total brings me right up here. 12 and a half seconds over, also known as 37 and a half, will bring me back to the center line. And then at 50, I will be back down at 1 meter. So I could repeat this pattern. Every 12 and a half seconds, I would go to the next key point. And then I can show you about what their graph would look like as they ride this Ferris wheel. Okay, so that's about what their, if we had to do a sketch of their graph. And it's not always necessary to do that graph, but it can always, shed some light on what the picture is going to look like.